In this section, we are going to talk about the fundamental theorem of calculus. What this theorem does is that it's going to connect what we have learned before, derivative, and what we are learning right now, integrals. Let's take a look at what the statements say. So the theorem, at least the first part of the theorem, state that if f is a continuous function on the closed interval a to b, then the function g defined by g of x equal to the integral of f of t dt from a to x, where x is going to be somewhere between a and b. G is going to be a continuous function on ab, and as well as being differentiable on ab. And the derivative of g is the same as the inner function, f of x. What you can think about this is essentially the derivative and the integral are opposite operation. So what does this mean? This means that, well, if you take an integral of a function f, and then you take the derivative of the integral, you should get back to where you started. That is precisely what this statement is saying. And of course, we have already seen this statement before, back in 4.9, and we'll talk more about that when we go to the second part of this theorem. We'll go to the second part of the fundamental theorem of calculus. For now, let's take a look at some example. So in this first example, we want to find the derivative of g of x, where g of x is defined as this integral. So keep in mind, from the fundamental theorem of calculus, part 1, the derivative of g of x is simply equal to f of x. In this case, what that means is that the derivative of g of x is simply the square root of 1 plus x squared, not t squared. And then we're done. That's it. The derivative of an integral is the inner function. Now, there are different kind of function that you can do with. Let's take a look at another one. H of x is equal to the integral from 1 to x to the 4th of the secant of t dt. Now, the fundamental theorem of calculus only states what happened when the upper limit of integration is equal to x. It did not state what is going to happen when it's not just x, when it's x to the 4th, when it's e to the x, when it's some other function. So what we are going to do is we are going to do some substitution. Meaning, let's, instead of writing x to the 4th, replace that with a u and take the derivative with respect to du. And then take the derivative of u with respect to x. Because what does this mean? This means that the first part, this now satisfies, sorry, that's a t right there. The first part now satisfies the fundamental theorem of calculus, meaning h prime is going to be secant of u. Sorry, that's an h prime right there. And the second part, well, the derivative of u, where in this case u is x to the 4th. So what is the derivative of x to the 4th with respect to x? Bring down the exponent, subtract 1 from the exponent, So in this case, we are going to get 4x cubed, and then replace the u with x as well. So for number 2, there's actually a more general formula that you can follow. For number 2, you can think of it as the following. The derivative of an integral where the upper limit of integration might not be just x, but it might be some other function, that is going to be f of t dt is going to be u of x, the function evaluated at whatever the upper limit of integration might be, and the derivative of u of x. Let's do another example like that. Okay, so we want to find h prime. Fundamental calculus say that we can take just the inner function, replace it with the upper limit of integration, and then take the derivative of the upper limit of integration, because in this case it's not just x. And even if it was x, if you take the derivative of x, that's going to give you just 1. So it really doesn't matter. In this case, the natural log and the e cancel out. The derivative of e to the x is still e to the x. And that's the solution. For this next problem, we will have to apply some property of integrals to be able to solve the problem. The function is f of x is equal to the integral from x to pi of the square root of 1 plus secant t dt. The fundamental theorem of calculus state what happened when the limit of integration, the upper limit of integration, is x, not a constant. What this means is that if we do have a variable in the lower limit of integration, we simply swap the place of the two, swap the upper and lower limit of integration. And when we swap the limit of integration, we introduce a negative. This is just going to be standard. It's just a straight up application of the theorem. So it's going to be negative, the inside, replace that with the upper limit of integration, and then the derivative of the upper limit of integration. In this case, it's just x, so it's just going to be 1. Again, just note that if f of x is equal to the integral from a to x, sorry, not a to x, a to some function in terms of x, of little f of t dt, then how do you find the derivative? Well, the derivative is going to be the inner function, replace that with the upper limit of integration, and then the derivative of the upper limit of integration. And that is the fundamental theorem of calculus, part 1.